So the next talk will be given by Vincent Foustoul from IRAP here in Toulouse about a sample of good miliparsec separation massive black hole binaries.
Hello, can you hear me? Okay, nice. So, hello everyone, my name is Vincent Foustoul. I'm a third year PhD student working here in Toulouse under the supervision of Nathalie Webb. And today I'll be talking about the work that I've done during my PhD. This is the work that I've been doing in collaboration with all these people that you can see here. So first, let me introduce you with a bit of context. So as Martha already presented this morning, the evolution formation of supermassive black hole is still an open question. Even more since the launch of the James Webb Space Telescope, as it keeps discovering more and more of these little red dots. We have possible scenarios to explain the supermassive black holes that we can see today. The three different channels create black hole seeds of different mass that will then grow via episodes of growth, via episodes of accretion and mergers. And these mergers are the events that are targeted by LISA, but before the launch of LISA, it is still possible to make some headway into the evolution of supermassive black holes thanks to the PTA experiment. So we've already had some talk about PTA, but just to refresh your memory, the pulsar timing array probed the lower end of the frequency, the lower end of the gravitational wave spectrum in the nanohertz regime, which corresponds to binary black holes in the mass range above 10 to the 8 solar masses. And in 2023, the PTA collaborations published a series of papers showing that they might have evidence for gravitational wave signal in their data, hinting that supermassive black holes can form binaries. But how can we detect these binaries? So, as Alessia already talked about earlier. Okay. So when massive black hole binary form tight binaries, we expect to see circumbinary disks around the whole binary and mini disks around each supermassive black hole. We also expect to see accretion streams coming from the circumbinary disks that will fuel each of these mini disks here, you can see here. And all of these components will create some variability in the light curve. So coming from different effects, coming from a relativistic Doppler effect when the two supermassive black holes orbit around each other, we expect the light from the mini disks to be periodically boosted. Also, it has been shown that another density can grow in the inner edge of the circumbinary disk, that you can see here on the plot, that will also create some variability during its orbit in the CBD. And finally, the secondary black hole orbits a little bit closer to the secondary disk and will accrete a little bit more of gas through the accretion streams that will also create some variability during its orbit. So also from these massive black hole binary mergers, we should be able to detect asymmetries in the shapes of emission line profiles and systematic and monotonic changes in the profile shapes due to the orbit of the two AGNs. You can see here the asymmetries of one of the supersec massive black hole binary candidates that has been proposed by Renaud and collaborators in 2016. And these kind of asymmetries and double-peaked emission lines should be also detected at other wavelengths. Sevanini and collaborators in 2015 proposed the supersec massive black hole binary from double-peaked emission line of iron K alpha emission lines in the X-ray spectrum of these sources. We expect from massive black hole binaries to have this kind of spectra, so a multi-component thermal emission coming from each of the parts of the system, so namely the primary and secondary mini disks, the accretion streams, and the circumbinary disks. And at higher energy, we also expect to see a non-thermal emission coming from the corona of the AGN. This is really similar to a type 1 AGN spectra. So just to remind you, for those of you who don't know, type 1 AGN are AGN for which the UV angle is such that we can see directly the central engine in the system, while type 2 AGN are AGN for which we can see through the absorbing material around the black hole. Keep that in mind for the rest of the presentation because I will talk about it later. But so how can we search for closed massive black hole binary? So in 2015, Graham and collaborators made a systematic search for periodic variability in the CRTS survey, and found 111 candidates. You can see here the light curve of 4 of these candidates. You can see that the period is quite large, around 2.5 to 3 years, and the modulation is quite low, around 1.1 to 1.2 amplitude, so it's really difficult to find this kind of modulations. And however, for this for AGN, we expect also to see a red noise process due to the turbulent accretion motion in the disk. So in 2016, Von and collaborators showed that this kind of variability can also be explained in single AGN. As you can see here, the light curve of one of these candidates, and on the panel B and C, the light red curve can clearly explain the variability that we see in the data. And in panel B and C, these are two different red noise processes. This is a bending power law spectrum light curve on the panel B and a damped random walk light curve on panel C. So the main focus of our work was to complete the light curve with more recent data in order to make sure that the variability is sustained over multiple set of observations, to make sure that this is actually a variability coming from binary and not due to a red noise process. So we used two different catalogs, the Katana Transient Survey, or CRTS, with observations made by 3 different telescopes, the Monthly Survey, Katana Sky Survey, and Siding Spring Survey. We used observations between 2005 and 2015 V-band. And this catalog contains around 500 million objects. And the second catalog that we used is the Zwicky Transient Facility, or ZTF, with observations made by the Palomar Observatory and observations that started in 2017 and are still ongoing in RG and I filters. This catalog is way bigger than CRTS1, as it contains around 7 billion sources in the data release that we used. So we completed the light curve with with the 2 sets of observations, with the CRTS observations and ZTF observations, and we fitted the world light curve with sinusoidal modulation. As you can see here on the left-hand side plot, these are 2 candidates that were proposed by Graham and collaborators in 2015. And you can clearly see on the top light curve that the variability is not the same between the 2 datasets. So we discarded this candidate as a possible massive black hole binary and attributed this variability to red noise. While on the bottom light curve, the variability is smoothly sustained over the 2 datasets. So doing that, we confirmed the periodicity for 26 candidates from Graham and collaborators, and found 10 more candidates from another catalog of ZTF variable sources. Also, in order to lend more support to the periods, we computed the generalized long-scale parallelogram for each of our candidates and find similar periods. As I told you earlier, so we expect to see a damped red noise process in AGNs. So we wanted to test whether or not we could retrieve the same periodicity if we injected a red noise process in the light curve. So we modeled a damped random walk light curve, damped random walk process in the light curve with Gaussian processes and find similar periods. We can find here the light curve of one of these candidates. And we tested if one of the models between a damped random walk light curve with and without sun modulations could be preferred by computing the base factor of the 2 models. However, due to the sparse data and the low signal to noise ratio, the base factor remains low for the candidates, even if we add by hand a sign into the data. So we cannot firmly say that one of the models is preferred, and this asks for more observations. So to speak about the results, we have found 36 candidates with reliable periods showing between 3 to 5 cycles. The periods that we found are the same with the different techniques that we used. So namely the long scale period, the periods found without the red noise and with red noise. You can see here on the plot that the periods coincide with each other considering their uncertainties. And we calculated the separation distribution of our candidates if this is a circular orbit and the same mass between the two supermassive black holes. So we have separations between 3 and 14 milliparsec approximately. We compared our results with simulations, and we computed the expected number of binaries at redshift below 1, considering an homogeneous distribution of binaries in the universe. Doing so, we expect around 21 subparsec separation binaries at redshift below 1, which is also compatible. Oh, okay. Compatible with predictions. We have here the histogram of the mass distribution of our candidates, which shifts toward high values, which is also expected by simulations. We asked X-ray observations for one of our candidates, and we got XM Newton and new star observation, joint XM Newton and new star observation for this candidate. This is located at a redshift of 1.3, so 1.23, so pretty high. The main idea was to see whether or not we could see a double peaked K-alpha line in the spectrum. However, due to the large redshift of the source, we cannot resolve the emission lines in the spectrum. And this is where Athena will be very useful to identify massive black hole binary. You can see here the X-ray spectrum of these candidates. So it's well modeled by a thermal disk and a soft access modeled by a thermal disk and a power law. The absorption is negligible, so it's really typical for a type 1 AGN X-ray spectra. And we took a look at the RGS data for these objects, which is high resolution spectrograph on board of XM and Newton. And you can see here the background substrate RGS spectrum for this object. We should be able to detect, we can be able to identify 3 emission lines, despite the low counts in the spectra due to the high redshift of the source. So the 3 emission lines at 37, 48, and 50 keV respectively. We tested whether or not this the significance of these lines. So we computed 10,000 spectra with only continuum and tested the improvement of the statistic if we add the lines in the simulated spectra. And as you can see on the right-hand side plot, the improvement of the statistic cannot be reproduced by continuum-only spectra. So these lines are really detected, and they correspond in the source frame to iron L-shell transitions, which is often observed in type 2 AGNs. But as I told you earlier, this is a type 1 AGN X-ray spectra. So these lines might be generated by a second AGN of type 2 that is obscured and cannot be seen in the spectra. So that's our main results from these observations. And I leave you here with my conclusions.
Good, Vincent. Time for a few questions for Vincent.
Oh, very nice talk. Concerning your fit with a new star and so you are talking about a soft access. That's the point here at
Yeah, it's not really well.
You fit with what with
thermal disk, with
and
black body disk.
And the temperature you obtain.
I don't have the temperature right now, but I can show you after.
Okay, just because so if it is at a redshift of 1, this is the point. So you because the temperature. Oh yeah, with this temperature, this black body, I don't know exactly, but it should be half of the standard temperature that we see in local AGN, right?
Okay. Yeah.
I don't know. I mean, this is a question, but
I can't really tell you a precise answer, but I can show you the temperature of the thermal disk interaction.
Thank you.
Thank you. Your question?
Thank you for the nice talk. I was wondering about PTA. And so could you expand a little bit more on which of your sources are potentially PTA candidates? And also there's a question maybe for PTA people is how does the sensitivity of PTA change for targeted search versus agnostic search for a single source?
So yeah, we've started a collaboration with people working in the PTA collaboration, and we've started targeted search for sources at redshift below 1 in our sample, but that's for continuous wave candidates, but that's the only thing that we're doing right now.
But how loud do you expect them to be in PTA? Because if you have a candidate, you know basically almost everything you need to know, right? To know how strong the signal would be in PTA. So do you really strongly expect to see them in current or future PTA data, or?
Well, I can't really say. I can't really say, sorry, but I guess yes, we should they should be able to pop up in the PTA spectrum. I hope so.
Thank you. And sure.
To your question, yes, if we can do a targeted search in PTA, and it's what, for example, Hippolyte is doing at
Yes.
ACME, we're working with Vincent, you should have a much better base factor than just searching via randomly via the parameter, because you really target the source that you want, so you can compute the base factor clearly, this model with this source against the rest.
Thank you. Yeah.
Thank you for your talk. I have a question. You showed the visible, so the optical light curves for your sources. Did you look into the Fermi light curves? So are gamma rays expected from the sources as well?
Gamma rays. I'm not sure about gamma rays, but yeah, we didn't look at higher energies light curve for these objects. But I guess the gamma rays should be emitted from the jets, right? I'm not sure though. But we
Very
did,
different model.
I'm not. I did not look at all at the gamma ray light curves. So, but I know that people already search for periodicities in other light curves, in other wavelengths for super-sec mini-black hole candidates. So this could be something that we should be probing in the future. Yeah. Yeah, we started a search in XM Newton as well to find super-sec binaries in observations.
So we have time for a last question. Vincent? Not. Let's move to the last talk of this morning session. Thank you again, Vincent.